So we're going to start the lecture a bit late because we had a discussion here in class. So a couple of things before we start. We're going to recap, or we're going to finalize the last couple of slides on stresses and strains before we get into moment of inertia. And before that, I want to have a couple of things. So the in-class exams are cancelled. So cancelled. What we do is take-home exam. And you get something between 24 to 48 hours time. Probably I will release it on Friday and then be done Sunday at noon. Something like that. Maybe Monday 9 a.m. I'll make an announcement of that, so just take it in consideration. And the reason is because some people that are doing online courses, it's just too complicated to align everybody's needs to it, and I think a take-home exam will solve a lot of issues. With that said, no book questions because of this. And there will be probably a bit more, since you got like 48 hours, 24 to 48 hours, there will probably be 5 to 6 questions. Okay, and instead of just focusing on stresses and engineering stress, 2D problems like the area stress functions will also be included. But I'll make a post about that, so for those online, you don't have to take time off if you're working, and you don't have to prep anything else. So we do a take-home exam. For the final, I'll make a post about that as well. That will still be in class. And advise this everybody that can make it, even though if you have to skip another class, please email that professor to get an exception for that one class. If they're being a pain in the ass or they're making difficulties, put me in that CC, and I can talk to that professor as well, just to showcase that the final exam is just one opportunity. So I would like to have everybody in class, and there will be a couple of students that cannot attend. Either they're working or they have their health issues, so we don't want to risk their health with it. And those will basically get the exam at a different time remotely. And it will be a different exam for them as well. So, okay. With that said, before we continue, so last week we left off at the last problem. That was an area stress function problem. We had some boundary conditions, and let me see, we had phi given as ax squared plus bx squared y plus cy to the power 3 plus d 5 minus y to the 5th. And then from area stress function, we said, okay, we have a function phi, and by definition, our sigma x is the second derivative with respect to y. Our sigma y is the second derivative with respect to x. And our negative tau xy is the derivative of a function phi with respect to x and y. And in order to satisfy all these simultaneously, we must have our compatibility equation, and that's stated that a 4th power derivative of phi must be equal to 0. And I think for this function, we had a set of boundary condition given. So one side was clamped, y was pointing downward positive, x was pointing to the right positive, and at this edge, we had a distributed load. This height was h, this one was h, and this was q. So basically from our area stress function, if we basically plot this, take the derivative of with respect to our y, xx, and xy, we get the following. We get sigma x equal to 6c plus 30d x squared y minus 20d y to the power 3, sigma y, 2a plus 2by plus 10d y to the power 3. Let me see, xx, yeah, makes sense. Negative tau xy. We get 2bx plus 30 dx y squared. Let's call this equation 1, equation 2, equation 3. And simultaneously, this was also satisfied. So I'll just ignore that for a second. This is satisfied. We plug it in. So we have given our boundary conditions. So we know a couple of things. We know that the stress is at basically negative y. So the stress, if we look at this figure, so our boundary conditions are defined at, say, y is equal to h. So here, this location. Then our sigma y is equal to 0 because there's no stresses here. At y is equal to negative h, that's this top side. Sigma y must be equal to q because q is pointing downward, there's positive directions. And what we also know is at this side we have a free edge. So at y is equal to plus minus h, our shear stress xy is equal to 0. So if we use these two conditions and we plug it into this, so boundary condition 1 and 2 into equation 2, let's call this circles and these are just numbers. What we get is 2a plus 2b, and let's do this one first. This becomes an h plus 10 to the power dh cubed is 0. And for the second one, we get 2a minus 2bh minus 10 dh to the power 3 is equal to q. So we can subtract this equation or this equation from that equation, or we can add it together actually, it's better. Then what we get is 4a is q, therefore a must be q over 4. So that's our first value that we determined. Then secondly, what we do is, then we can use our so boundary condition 3 into basically the third equation. Now we get that 2bx plus 30 dx, and then doesn't matter, squared, it becomes h squared anyways, is equal to 0. So in this case, I dropped the x last time, so that got me a remaining x. Because you have bx here, I didn't notice that, and you have an x here, you can basically drop the x's. So now you can get b is equal to minus 15 dh squared. And then as lastly, we said also we need another boundary condition, and we set the moment. So the moment at the moment 0 when x is equal to 0, and the moment is defined by the integral minus h to h, sigma y, sigma x, multiplied by y dy. And if you evaluate that integral, what we get is we get 2c to the power y cubed, or 2cy cubed, minus 4d y to the power 5, and evaluate minus h to h. And that basically gives us c minus 2d h squared is equal to 0. So what we can now do is we can plug our a value. Let's see, this should be d. Yeah. So we can plug our A value into equation 2. We can get our B in the equation 2 as well. So basically we have Q here, we have D here, D there. So we can basically solve for this at the boundary condition. And then we have enough boundary conditions and variables to solve. And then we get all the different, all our coefficients. In this case, A still be equal to Q4, B is equal to 3Q over 8, H, and C is equal to minus Q over 20H, and then D is equal to minus Q over 40H cubed. So that's basically the system how you basically solve such an area stress function. So regardless of any function given, you basically define your stresses sigma x, sigma y, and sigma z. You check your compatibility equation, the biharmonic equation. This is written out to be x, so the fourth partial derivative with respect to x, second partial derivative or fourth derivative with x squared, y squared, and then the fourth derivative with respect to y is equal to 0. And if you plug this in, if that satisfies, that means your function f satisfies your compatibility equation and your stress equilibrium equations, and then you can solve for coefficients based on a given boundary condition. And boundary conditions, that's basically where it comes in. And the trickiest part in this solving such a problem is getting the correct boundary conditions out of it. So of course you want to go for where stresses are equal to 0 or stress are equal to a quantity that you know. So for example, we did a couple of locations. We used our first location because there we know that y is equal to h, sigma y is equal to 0. At this location, at y is equal to minus h, we know that sigma y must be equal to the distributed stress applied, so that's equal to q. Note that q is pointing downward positive, so that's therefore it's positive. We know that on this side we have a shear stress, but there's no shear stress given as boundary condition, so we know that tau xy is equal to 0. And again, on this side we have a free edge, so we know that if there's a moment applied here, that must be 0 as well. And the moment, of course, is defined by your integral from your bonds, say minus h to h of sigma y, sigma x, multiplied by y, differentiated with respect to y. Yes?
How come shear stress is 0?
Free edge and no shear stress is given.
Oh.
And how do we know if y equals h, sigma y equals 0? Does the force not transfer through the body? Or is that a separate body?
Yeah.
Yes. I mean,
So you have basically a boundary condition, a free edge, and no stresses of the free edge.
okay.
So that's the reason you can assume it's 0. So yeah, there's technically, of course, if you're doing full stress analysis, we'll see if you have this as your body clamped and you have a load in upon it, there will be something like this.
Yeah.
So yeah, we don't go into that detail.
Okay. So if there's
So no deformations.
Okay.
Okay. With that said, we can basically go to our next topic, which is basically the topic scheduled for today, and that's basically moment of inertia. We'll probably take 2 lectures for that instead of 1. We'll see how far we get today, and then we'll continue on Wednesday, and if we finish early on Wednesday, we just finish early. Because we don't do any in-class exams, we basically save 2 lectures, so this will not delay us in any manner, even if we take 2 lectures to discuss the moment of inertia.
Excuse me, sir, quick
Yes.
question. Just looking at the lecture notes, I see it was whenever y equals h, sigma y equals 0. So and that's just setting the equation we found for sigma y, the double derivative of
Yes.
xx. So if the force was in the x direction, we would do the same with sigma x.
So what you often will see that during the, if you have the boundary condition again, you can come up with more boundary conditions to solve it. So you go for the simplest equations. So if you have given And the simplest boundary condition is when you can set something equal to 0 or given to a known value. So yes, if this was ignored and you had something like this, pulling on it, then yes, you go for sigma x and setting that equal to that quantity.
Okay.
And then you know that sigma y on the top is equal to 0,
Okay.
etc.
Got it.
And then you also know that, assuming there is no deformation, of course, that the tau xy and the top surface and bottom surface corresponding to a value given for x and y is equal to 0 as well. So you probably can use multiple dimensions, multiple things to come up with it. So from previous, so for those basically online, so previous years I didn't do this as a separate topic, but I noticed there's a lot of people make mistakes in it, and it's quite, it's not something that you want to make mistakes in. It's very simple and just needs basically experience on how to solve it. And that's basically the concept of moment of inertia. What we'll see is that moment of inertia terms, xx, yy, and xy, they will basically pop up in all the equations that we're going to deal from now on. So in engineering bending stress, so in the next lecture series, lecture topic, we will derive our direct stresses that will be equal to our moment multiplied by y, our distance, and then xx. This is the simplest form. So xx pops up here. Once we go to our shear flow equation, we'll have our shear flow, which is equal to Ixx. This is the simplest one. Y from 0 to S. So it pops up again there. In torsion, you have a polar moment of inertia, so it pops up there as well in a slightly different form. So making a mistake here can complicate your life because sometimes things will cancel out. And in your case, if you make a mistake, things might not cancel out, so it may look more complex than it actually is. Or you just are dropping points or partial points while they're very simple to do. So that's basically the topic for today is, for this lecture topic, is to help you guys understand what the moment of inertias are a bit better and where it comes from the equations, and then hopefully prevent you making any mistakes. So I think in the lecture series I say, okay, well, let's assume that we have a canal or something that we want to cross, and we have a body of water, and we have basically a 2x4. Let's call this H and length and width. And we have two options. We can want to basically cross it, or we want to put the weight on it. So we have two options. We can use our 2x4 like this, horizontally, or we can put it vertically. Same dimensions, same L, same W. Which one will be better suited in this case? Second case. That's correct. And why?
Because it's less likely to bend.
But why was less likely to bend? But why was the moment of inertia? So the reason is you're definitely correct. So definitely case 2 is better. And the reason for that is, that's what you said, it's indeed less likely to bend, so the resistance to bending is greater. And the resistance to bending, if you basically drive neutral axis on which axis it would bend, so you can take that as I have a remote, I'm trying to bend it, so if I try to bend this remote, what will happen is there will be one axis, so basically, no, let me see, before and then after, this, exaggerated of course. So part of it will be compression, part of it will be in tension, and if you look through it actually, there will be through the thickness, there will be an intersection that basically doesn't deform. So this dotted line will be the same length as this on the dotted line. So that's, we can say that's basically the axis where we bend around. So if we look at the axis that we basically bend around, and we focus more material as further away from that axis. So we have, in this case, more materials away from the axis of bending. This basically yields better resistance to bending. So this one has relatively the axis to bending, so this is basically W/2. If you look at this side, W/2 is smaller than L/2. So this has basically, this is L, so this is L/2 at this location. We have a longer axis towards the bending axis, so that gives a little bit more resistance in bending. And that's basically the concept that that's basically the concept of moment of inertia. But having the concept of the moment of inertia, like, okay, we have more materials away from the axis of bending equals better resistance to bending. But we want to, of course, quantify that in such a manner and to have a clear picture, okay, geometry 1 is better than geometry 2. And for that, we want to basically come with something quantitatively. And to do so, basically what we look at, like we said earlier, we're looking at how much material and what's the distance towards, or what's the distance away from the axis of bending. So what we can do is basically can draw arbitrary shape. We define a certain axis, doesn't matter where currently, y, x, and we said, okay, we get a bender, we have better resistance to bending. If more material, if material is further away from the bending axis. Okay, so let's take a small element. This is our element dA as an area of dA, and we want to quantify how far it's away from the bending axis. And we take it with respect to x-axis in this case. So the distance away from the x-axis is equal to given y, say y1, or just call it y. So, and if we do that for a second element, like here, and a third element, and we basically do that for the whole cross-section, what we can do is we get a number of how materials are distributed away from the axis, and we can basically sum those all up, take the summation of dA y, and we get the quantity that we call the moment of inertia. And to indicate around which axis we're talking about around x-axis, we designate it with an x. So that will give us the quantity of moment of inertia. And we can repeat the same thing, but on a different axis. In this case, if we do it this same element, but on the y-axis, then we need the distance from dA to x. So in this case, moment of inertia on the y-axis will be equal to dA x. And of course, we can do what if we have a combination of the moment of inertia with respect to x and y. And in that case, what we do is moment of inertia with x and y. That will be dA x times y. So to the x-axis and to the y-axis. So if you want to do this a bit more precisely, instead of doing a summation-wise approach, we can do an integral approach. So you're transforming this to the integral. This means this is the integral over the area A of dA y squared. And so we take the integral over A, we write it as dA I'm missing squares. XY here. And we do the same for the other ones. So A, x squared, dA, and xy, dA. So that gives the definition about moment of inertia on the axis x, y, and z with respect to a given reference axis. So what we have to realize that these equations are valid around our chosen axis system of x, y. So valid for axis x, y. And we'll see later if we change this axis system, of course our numbers will change, and we will see that we can basically come up with an easier way to find how they change. Yes?
If you're bending around the y-axis, so we take the ixx. And if you're bending around the x-axis, we're talking about I lambda. Is that correct?
We're bending around the, can you repeat that again?
Then around the y-axis, we take the ixx.
No, we take the IYY. So this is bending around X, bending around Y, and XY. So to indicate that, say if you take your beam again, so you want to basically bend around this axis, right? So then the resistance of bending is defined by your element to that axis system, and that's differential with respect to X.
And what about xy?
XY is basically a combined bending around X and Y axis. So we'll get to that. This is a special one, and we'll see some conditions that this is more for when you have an asymmetric loading. Since you have, say for example, if you do just bending around X, you can use your moment, your XX, IXX. When you have a bending just in, say, in the Y plane, you can use your moment around YY. But what if you have combined bending? So there will be interaction between the moment around the X plane that affects the, as a contribution to the bending. Your bending around the X has contribution to the bending, say, around your Y plane, and this is your combined, this is your coupling coefficient, basically, that translate bending, that couples the bending in X also to Y, and vice versa. Let me see. And we see a couple of more different things. First of all, this is square. So regardless of what we have always a positive number. This is squared here, we have a positive number. And this one, it can be either positive or negative depending on its axis system. Let's look at this. Say, for example, if our axis system is 0, 0 here. So X in this direction is positive, Y is positive. So our moment of inertia in XY will be positive in this domain. Here we have X positive but Y negative. So X times Y will be negative. Here we have negative, negative, so that will be positive. And here we have negative in X, but positive in Y, so this will be negative as well. And of course, this is dependent on this axis system. Assume that we would change our axis system, and we would say, well, I want my axis to be here, 0, 0. Now we can see that YY and XX, because they're squared anyways, they will remain positive, and they're not affected by it. But now XY is positive everywhere, so this one will be positive. And of course, if you change our axis system to here, XY, XY, the tree system, they will all be negative. So in some cases, XY be either positive or negative, and this can be beneficial or disadvantage to you, to the case. Okay, so what we can do is, once we have our equations that define our moment of inertia, we can basically calculate what the moment of inertia of certain cross-sections are. And we can do that for a couple of different cross-sections. And we'll see that if we do that for, say, our first case, remember, if you calculate the moment of inertia for a given beam length L and width W, and we just transform that so this what we compare to. We call this 1. Our moment of inertia on, say, case 1 is equal to 1. If we just switch it over, we'll see for the same dimensions, case 2, our moment of inertia on x, let's assume we bend it on that axis, will be 9 times bigger. And what we said about we get better resistance to bending if we move away our materials further away from the axis. What we can do is keep in the same area, same area A. If we do that and we just put more material to the top and more material to the bottom, like an I-beam, but have them connected with some residual, and we have the same total area, in this case we will get a moment of inertia of 27.6 actually. So now we can play around with the geometry and we can basically optimize our structure for bending or resistance to bending. And that's the reason why I see I-beams significantly in construction, especially in skyscrapers and other civil engineering structures, because the moment of inertia is significantly higher than the other two for the same number of material. And the material is the same, then the weight is the same, so basically can reduce, and if you only need a certain moment of inertia, say 20, now I can reduce the area so I can make this thinner and save weight. And in aircraft, we don't see I-beams. What we see is stiffeners and strainers, and those are basically local reinforcements. Say, for example, we have a plate, and these are like, what, 2 millimeters thick. But if you bend it, it's quite flimsy. So instead of, we can either put in I-beams, like small I-beams, or small L-beams, let's do for L's, at certain locations. And then we do another one. And this basically does the same trick. Instead of, if you have a given load requirement, instead of increasing the thickness to, say, to 10 or higher, what we can do is we can add local reinforcements. And if you now calculate the picture, the moment of inertia of this plate, say the IXX of the plate, will be basically the IXS of your no stiffeners plus n times the IXX of one stiffener. So you can increase your stiffener, your moment of inertia, by just adding local reinforcements, and that way you can keep your thickness to the desired thickness. Maybe you're limited by weight, and you increase the weight a bit by adding stiffness, but they're still significantly lower than increasing the plate thickness in order to get the same moment of inertia. And this brings to a nice concept of the moment of inertia. We can easily add them up. And the opposite to that as well. We can also subtract moment of inertia. So we can superposition moment of inertia terms upon each other to get that total moment of inertia. So if you have a very complex structure, say, now just trying something like this, what you can do is you can say, well, I have this plate here. So this is 1, this is 2, this is 3, this is 4, this is 5. So moment of inertia of the whole is summation of the moment of inertia of the individuals. Of part 1, 2, 3, 4, and 5 combined. And because this is true, we can now basically reduce the complexity of our moment of inertia. Instead of figuring out what the moment of inertia, like in the integral, is for this structure, say if an element dA with x for given element given axis system, we can basically see that this structure, this complex structure, is nothing else than straight lines. And the moment of inertia of these two are very simple to calculate. Okay? So let's do that actually. We take the the moment of inertia of the most common just from a rectangle, and we see how we can calculate that. So let's get some dimensions. No, I don't have any dimensions, but it doesn't matter. So let's calculate. We have a block. Like we said earlier, this depends on your axis system. So we call this y and x, and we say this corresponds with our centroid C. So I assume you guys know how to calculate the centroid of an area or from block. And now let's evaluate the moment of inertia around x. We said that's equal to the area integral of y squared dA. The area integral can be replaced by two integrals around x and y. So we get x squared dx dy. We can decouple that into dx y squared y. And we can now evaluate that. Let's give it a couple of dimensions. We call this width d, and we call this the height h, and this is of course h over 2, and this is b over 2, one area. Now let's evaluate our integral. So for x, we know we have to cross the whole width. So we go from minus b over 2 to plus b over 2, because with respect to this coordinate system xy. So our integral bounds for the x count part is minus b over 2 to b over 2 dx. And the integral of y is crossed from here to there. So that's minus h over 2 to h over 2 y squared dy. So integral with respect to x, that will be just x. So, and then what we get is, let's evaluate one by one. What we get is x, evaluate minus b over 2 to plus b over 2. And what we get is, if we evaluate this, we get just b. And then we get the integral of 1/3 y to the power of 3, evaluate minus h over 2 to plus h over 2. What we get is here is ah b on this part, and then we get multiplied by 1 over 3, and then we get h over 2 to the power of 3 minus h over 2 to the power of 3. This is nothing else than 1/8 minus minus is plus 1/8, so this is 1/4 h to the power of 3 multiplied by this, and then we get 1 over 12 b times h to the power of 3. So that's evaluating the integral. That's one way of calculating this. And of course we can do the same thing for yy. And what we see is that just the width and the height interchange. So yy will be 1/12 b cubed times h. Okay, now we go into our xy axis, and we'll see one unique property of our moment of inertia on xy already popping up. Let's put this here. And by y, what we get is, we do the same thing. You see this integral of a x y dA. That will be equal to double integral on x dx, integral on y dy. And then we can change the bounds, of course. So for x, we have b over 2 to minus b over 2, minus b over 2 to b over 2, and for y we have h over 2 and minus h over 2. And what we get is, of course, we evaluate the integral, get 1/2 x squared, evaluated at the bounds, 1/2 y squared, evaluated its bound. And now we can basically collect terms. What we see is minus 1/2 b squared, so we get b over 2 squared minus b over 2 squared, blah, blah, blah. And then we get y over 2, or h over 2 squared minus h over 2, or minus h over 2 squared. So what we get here is squared, so it becomes a plus. So this is b over 2 minus b squared over 4 minus b squared over 4. Half. Then we get here h over 4, h squared over 4 minus h squared over 4. Half here. Multiplication here. This, of course, is equal to 0. This part is equal to 0. So Ixy is equal to 0. And what we can see is the reason why it's equal to 0 is because you have a symmetric axis to it. We can see that the contribution from from the integral, from going from one side to the other side, was basically symmetric, and that gives us a 0 condition. So let's assume that this was not a square, so it was not doubly symmetric. So we didn't have 2 axes of symmetry, but it was more like a C-section. Yeah. So we still have 1 axis of symmetry. So that would mean that in this case, yeah, this part will be equal to 0. So once you have at least 1 axis of symmetry, your moment of inertia is equal to 0. So in this case, we had 0, and it's always true if you have an axis of symmetry. So 1 or 2 axes. So you can see that your calculations often can reduce in complexity if you can spot that your cross-section is equal symmetric. You don't have to do this evaluation of this integral. You can just state, do the symmetry, moment of inertia on xy is equal to 0, and that's sufficient. Yes?
What is the practical example or explanation of Ixy is equal to 0? Like,
it basically cancels each other out. That's again to do with the fact.
So what if I bend it in the xy direction? What's going to happen? There's basically nothing.
What this practically means is if I have a bending moment through bending, say if I bend this on x, this plot is a bit off. Say I have a C-section, right? And this is my, let's call this x, let's call this z for simplicity. And then this is our y-axis. Normally we said if it's not symmetric, if I have a moment around x, right, I will add, so if I bend this, normally we just see a bending around x. So this then would just bend around like this. Right? So we do a pure bending. So there's no coupling. If I bend it in the other direction, it would basically bend all the way that side. If it's not symmetric, that means if I bend it around x, there will be some bending around the y-axis or the z-axis simultaneously, even though there's no bending force in the y and z plane. That's basically the practical meaning of it. So if my cross-section is symmetric and it's just on the bending, we'll basically bend only around that axis. So I don't have a decoupling, coupling moment to it.
If my IXY is 0, so if I'm bending in the x direction, there will be no significance.
They will only be bending in the,
X direction.
basically in the x
And
direction.
if I have some value of x, y.
So if this was like this, like a small lip, yes, then you will see that there's a bending and a slight twist to it. Even though you only bend in around the moment, around the x-axis. And that's the reason why symmetry is very important. You can reduce the complexity of the bending. And you can prevent, say, sudden things from happening if you didn't take that into your consideration in your calculations. So we did now the bending, or we derived the moment of inertia around x, y, y, and xy, and we started at basically 0. And this was valid for this basically centroidal axis. So what if our centroid is now, our axis system is somewhere here? So one way to do it is actually to rederive the equations. And we can do that quickly for IXX only. So we have the A, y squared A, we get as, in this case, the bond of y remains the same, but the bonds of x goes from 0 to b, instead of minus b over 2 to b over 2. And we can do that. So we get dx, y squared dy, so this becomes x from 0 to b, and 1/3 y to the power 3 from minus h over 2. No, sorry. This bond also, of course, changes. This changes from 0 to h, so this goes from 0 to h. So what we get is b multiplied by 1/3, and then we get y h to the power 3. And our equation becomes 1/3 b h to the power 3. So we have a difference here. So that's how, so it's important to know that your moment of inertia will be dependent on your coordinate system that you choose. So the question becomes, okay, do I every time if I change coordinate system, do I have to evaluate the interval? No, you do luckily do not have to do it. And because of that is, and the reason for that is, it's called the Steiner's theorem, or Steiner's the parallel axis theorem. It basically means that the moment of inertia on C, let's call this A actually, the moment of inertia on A is equal to the moment of inertia of the cross section around the centroidal axis C, plus the area multiplied by the distance squared, and that distance is from one axis to the other axis, to the parallel axis. This is D. And we can actually implement this directly. We said, okay, let's do this using this equation. We said we already had known this before, centroidal axis, 1 over 12, BH squared. The area is BH, and the distance from the centroid to point A is D, which is equal to H over 2. So H over 2 squared. So that's equal to H squared over 4. And if we do that, so we get this 1/12. Well, let's take out BH cubed. We have 1/12 plus 1/4. 1/4 is nothing else than 3/12. So 1/12 plus 3/12 is 4/12, which is 1/3. So these two are not the same, equal. And there's a much easier way to calculate the moment of inertia when the axis system changes. And the reason why it's significantly easier to calculate is because I'll go to the lecture slides for this. Okay. So for those online, go to lecture slides 15. Lecture slide will not pop up. And those on in class can look at it, the board. So a lot of those moment of inertia for common geometries are already determined, and you can find them just at the back of the book, or they're very easily calculated. So those moment of inertia is always defined through the centroidal axis, so through the centroid of the geometry. So now you can use the given known problems or the given known moment of inertias, and you can translate that to your axis system that you chose yourself. And that makes the calculations much easier. So this also, if you recall the example I gave you earlier, if I have this, and I say calculate the moment of inertia of this, this geometry here, what you can do is you can basically separate this into, like I did previously, into 5 components, and you can see that all the components are straight sections, either flat, say on the width, horizontal or vertically aligned. So in this section, it's nothing more than the moment of inertia. See, if you want to do the Ixx of 1/12 b times h cubed here as well. So now you can use this, and this will be valid for this section and its centroid, and will be valid for the top section and its centroid, and the bottom section at its centroid, and this flanges here also at its centroid. So this 1/12 is always valid at the corresponding centroid. So if you calculate the centroid of the geometry, and let's do that in red, centroid will probably lie somewhere here, let's say. Let's do it slightly off from this axis. Let's put it a bit close to this one. So what you can now do is you calculate the individual components and just add the parallel axis theorem for each and every one of them. So now this, the Ixx of this complex shape is equal to the Ixx of the individuals, Ixx on the centroid of the individuals, plus the corresponding standard terms, where D is always the axis towards the distance between the parallel axis. So if you do XX, that means your X distance, or in this case Y distance, from this location to that, from here will be downwards, this will be downwards, these two will be going up, and this one will also could be up. But the square is always positive, so it doesn't matter. And then you can calculate the moment of inertia on the entire cross-section. I think we have a couple more slides, but we'll save that for next lecture. And what I'll do is I will come up with a couple of examples that we can actually do together. There will be a couple of more lectures that will be heavily based on theory, especially when we get to the torsion side. But after that, a lot of things will be less derivations and more actual problem solving, and we'll try to do at least one example per lecture. So in the beginning, it will be a bit heavy on theory, like we haven't done any examples. But Wednesday, we'll continue finishing up this moment of inertia, and I will give a couple of examples that we just do in class. And once we get into engineering bending theory, we will have, I think, 1 or 2 lectures with a lot of derivations, and then go back more into problem solving, so you know actually what you can expect on the exams and what you can expect on the exam and the take-home exam. Okay, perfect. So we have 5 more minutes. Are there any questions? No? Okay, good. Thank you very much, and I will see you guys on Thursday, right? Yeah.